Good evening, and welcome to the Sleepless Scientist. Tonight's story drifts into why the universe seems to hate straight lines. If these calm explorations feel right, you're welcome to like and subscribe. Share in the comments where and when you're listening. It's heartwarming to see our circle. Now relax, dim the lights, and let's quietly set out. If your mind wanders, just let it. We'll still be here. Imagine for a moment that you are standing at a quiet railway platform late at night. The air smells faintly of steel and dust, and the lamps line up in a neat row above you, casting their light in narrow bars across the concrete. The track ahead stretches into the distance, two parallel ribbons of steel running perfectly straight, or at least that is how they appear. You know, of course, that if you were to follow them far enough they would begin to curve, guided by the lay of the land, the softness of the earth, and the decisions of the engineers who laid them down. Yet here, in this narrow slice of perspective, they seem flawless. A human-made attempt at a straight line, held together by bolts and gravel, and the stubborn insistence that the world can be tamed into geometry. Humans adore straight lines. We draw them on paper, measure them with rulers, stretch them across city blocks, and stack them in skyscrapers. Straightness, to us, feels like order. It feels like clarity, something dependable in a world that otherwise resists our neatness. We pave highways across valleys, string telephone wires taut, design the grid of a city so that its avenues intersect at right angles. It is no coincidence that we use words like direct or straightforward to describe not only geometry but also honesty and truth. A straight line seems to promise certainty, but the universe has its own opinions. Out beyond the reach of our surveyors' chains and architectural plans, nothing truly moves in perfect straightness. The planets do not travel in straight lines. Stars orbit in grand ellipses. Galaxies spiral in arcs of luminous dust. Rivers snake their way to the sea, and even a ray of light bends when it passes near a massive star. Straight lines are less a feature of reality than a feature of our imagination. They are convenient, they are tidy, but they are not how the cosmos prefers to draw. Think again of that railway platform. A clock hangs above the waiting passengers, ticking off seconds with reassuring precision. You might expect that clock to run the same no matter who looks at it, no matter whether the viewer is on the train or on the platform. Yet physics insists otherwise. If the train accelerates close to the speed of light, its onboard clock will slow compared to the platform clock. The straight line of time, which we so casually sketch as a simple arrow pointing forward, wavers and bends under motion. A moving second is not the same as a still one. Even in the one domain where we like to imagine straightness, time's steady march, the universe gently resists. This tension between our love of straight lines and the universe's refusal to honour them will be the thread of our journey tonight. We will explore why nature favours curves, spirals and webs. We will wander through Einstein's insights, where space-time itself curves around mass. We will pause among galaxies arranged in filaments like lace across the darkness, and we will trace the spirals of seashells and hurricanes. We will follow particles racing in accelerators, clocks carried around the world, and satellites circling the Earth, discovering again and again that the straight path is not the natural path. Why does this matter for you, sitting perhaps in your bed or on a quiet sofa? Because straightness is a comfort we invented, while curvature is the truth we live inside. Your body itself is a collection of arcs, the arch of your ribs, the loops of blood vessels, the spiraled staircase of DNA inside each cell. The air that fills your lungs flows along branching paths. The food you eat was once carried through twisted rivers, grown on plants that stretch toward the sun in subtle curves. To be alive is to participate in bending, and so, as you listen tonight, let your own thoughts curve as well. There is no need to hold them in strict alignment. If they drift sideways, spiral back to memories, or branch into half-formed dreams, that is not a failure of focus, but rather a harmony with the subject itself. The universe prefers curves. Your mind can too. Think of the track again, gleaming under the platform lights. To your eyes it seems straight. To your mind it suggests certainty, a line from here to there with no hesitation. Yet if you could step back far enough, you would see the Earth's roundness beneath it, the slow tilt of continents, even the curvature of space-time itself. The line you trusted as straight was never truly so. It was simply close enough for your limited vantage. Straightness is always an approximation, a story we tell ourselves for convenience, a lullaby to soften the wild geometry of existence. As we begin, keep that image close. The universe does not despise straight lines in the way a person might dislike a taste or a song. It simply does not deal in them. Straightness is our projection, while the cosmos keeps curving in its own way. Tonight we will follow those curves, listening to what they whisper. If you feel your eyelids grow heavy as we travel, that is perfectly fine. The universe has been weaving its spirals long before you, and it will continue long after. You may rest in its arcs. So let us step quietly from the imagined track onto the wider field of stars. Let us set aside, just for a while, our rulers and our graph paper. Here begins a journey not of lines but of loops, not of angles but of orbits. The straight line was always a gentle illusion, and now, together, we can watch it fade. When we begin a journey, we often like to know where it might lead, or at least what sort of landscapes we will pass through along the way. Tonight's journey is not one that needs a map in your hands or shoes on your feet, but it still benefits from a little orientation, a quiet sketch of what lies ahead. The subject we are following, this strange resistance of the universe to anything perfectly straight, is not a single idea to be solved in a sentence. It is more like a long path that winds through many regions of knowledge: physics, astronomy, biology, even philosophy, and each place adds its own kind of curve. So before we dive into those turns, let us pause together and look at the horizon of what we are about to explore. The aim of this story is not to overwhelm you with equations, nor to drown you in names and numbers. It is instead to gently reveal why things bend, why they spiral, why they branch, and why, whenever we humans draw something straight, the universe seems to lean over our shoulder and quietly round the corners. To do that, we will visit the great figures of science who first noticed that time itself can stretch and shrink, that light refuses to play by our common rules, and that gravity is not a tug in a single line downward, but a soft curvature in the fabric of reality. We will wander with Einstein as he discovers that space and time are partners rather than rivals, that mass can warp the very grid of existence, and that nothing, not even the fastest beam of light, can escape the subtle bending that results. Along the way, we will also look at the evidence that these curvatures are not simply theories scribbled on chalkboards, but truths that can be measured in the tick of a clock or the path of a particle. We will meet atomic clocks that circle the Earth and return with different times written in their faces. We will greet ghostly muons, particles that should die before they reach us, but that somehow survive thanks to time stretching along their journey. We will notice how satellites circling above our heads must constantly account for both their speed and their altitude, adjusting their clocks so that the maps on our phones remain trustworthy. Each of these experiments is a reminder that straight time and straight paths are illusions of convenience, while the deeper reality is always curved. But the scope of our story will not be confined to physics alone. Once we have listened to the way time and space bend, we will turn to the natural world around us and see how curves dominate there as well. Seashells wind themselves into spirals, hurricanes unfurl in wide arcs across the ocean, galaxies spin like pinwheels of light. Branching rivers carve through continents, trees split and split again into finer stems and leaves, lungs divide into bronchi and bronchioles until they become a forest of airways. Even the coastline of a country, seen from above, reveals fractal edges, never straight, always jagged or looping. The universe insists on patterns that distribute, that spread, that wander, rather than patterns that march in a single line. From there, our gaze will lift to the larger scales, to the cosmic web itself. Instead of stars scattered randomly, we find galaxies arranged like threads of lace across the void, woven into filaments and knots that remind us of tangled embroidery more than rigid scaffolding. Straight grids may suit our paper, but the cosmos has stitched something very different. A pattern of curves and filaments stretching over unimaginable distances. The story will not ignore the extremes either. We will venture near black holes, where time behaves so strangely that one observer sees it slow to a frozen halt, while another experiences a smooth continuation of life. We will rest for a moment on the surfaces of neutron stars, where time itself is bent by gravity to a degree that even light carries the evidence of dilation in its colour. We will listen to gravitational waves, ripples in the fabric of time and space that pass through us without resistance, leaving no straightness untouched. These extremes are not distant curiosities, they are the loudest examples of the same bending that shapes rivers and galaxies. Finally, our journey will draw into reflection. We will speak of simultaneity, of the fact that two events that seem at the same time for one person are not simultaneous for another. We will imagine light cones as lanterns in fog, showing which parts of the universe are reachable and which are forever beyond. We will explore the idea of the block universe, in which all moments exist together like a sculpture, our lives merely paths winding through its volume. And we will end by turning the lens back onto ourselves, onto the straight lines we cherish in architecture and city plans, and noticing how even those lines bend under the weight of time, of memory, and of human living. So the aim tonight is not simply to declare that the universe dislikes straightness, as though it were a matter of taste, but to show how deeply woven that preference is. It is written into space-time itself, into the paths of particles, into the structures of galaxies, into the growth of shells, branches and lungs, and into the way your own story bends through the hours. Our exploration is not about replacing straightness with curves, but about listening to the curves already there. If at any point during this voyage your eyes close and you drift away, that is perfectly all right. The spirals of galaxies do not end if you nap, nor do the branches of trees halt their growth. You will have joined them in bending, your mind curling inward like a leaf at night. The story will continue whether you are awake or asleep, just as the universe has always continued its curving, whether or not anyone was there to draw a line. And so, with this mapless map, with this aim that is not to reach a destination but to follow a path, we can begin. We will follow curves, where they lead, linger where time slows, and rest in the spirals of thought and cosmos alike. Straightness may belong to our tools and our diagrams, but tonight, here, we leave the rulers behind. The aim is simply to listen to how the universe bends. If you close your eyes for a moment and imagine space, perhaps you see a great black canvas, dotted here and there with points of light, a kind of endless stage upon which stars drift and galaxies gather. Now, if you imagine time, perhaps you picture something different entirely. A line with an arrow pointing forward, the ticking of a clock, or the slow procession of days turning into years. For much of human history, that is how we treated these two. Space on one hand, time on the other. Two separate realms. One could be measured with rulers and compasses, the other with clocks and calendars. They seemed as different as land and sky. Yet the universe is rarely content with our neat divisions. It took the mind of Albert Einstein to dissolve the boundary between them. To him, space and time were not separate domains, but one fabric, one interwoven stage upon which reality unfolds. The word that came to describe this unity is space-time. When you picture it, resist the urge to see it as two different materials stitched together. Think instead of a single cloth, perhaps like a woven blanket where threads of different colours cross and intertwine so thoroughly that you cannot pull one out without tugging on the other. Space and time are not stitched neighbours, they are partners woven into the same loom. The idea may sound abstract, but let's find a gentler entry. Imagine you're watching a bird in flight. You could describe where the bird is, 10 metres above a tree gliding eastward. But that description is incomplete, because to know its true position, you also need the when. A bird flying east yesterday is not the same as one flying east now. Space without time is a still photograph, but the bird's existence is not a photograph, it is a film. And so, whenever you describe anything in the universe, an atom, a star, yourself, you're really describing a point in space-time, a location in both where and when. You're not simply here, you're here now. Remove either half, and the sentence makes no sense. Space-time is not only a merging of coordinates, it is also a stage that bends. Einstein showed that mass and energy curve space-time, and that curvature is what we experience as gravity. The metaphor often given is of a heavy ball resting on a stretched sheet of fabric, creating a dip into which smaller balls roll. This image is imperfect, because the sheet relies on gravity itself to pull the ball downward, but as a picture, it still helps us imagine how space-time is not rigid, but elastic. The Earth curves space-time around it, and the Moon falls into that curve, circling endlessly. You are, right now, moving along a curved groove in space-time carved by the mass of our planet. To walk through this gently, think of yourself standing on a hillside. Gravity pulls you downhill, but another way to phrase it is to say that the hill itself is curved and you're simply following the slope. In the same way, when an apple falls from a tree, it is not yanked downward by an invisible string, but simply following the slope of space-time created by the Earth's presence. The apple is rolling, invisibly, down a hill you cannot see. Now here is where straight lines sneak back into the conversation. In Euclidean geometry, the geometry you learned in school, straight lines were the shortest distance between 2 points. They were dependable, clear, eternal. But in Einstein's geometry, the universe itself can curve, and so the straightest path is no longer what it once was. On a curved surface, the straightest possible line is called a geodesic. Picture a globe of the Earth. The equator is a geodesic. The great circle routes that airplanes take across the Atlantic, curved on a flat map, are also geodesics. They are straight in the sense that they are the shortest distance across the curve. Likewise, in space-time, particles and planets and even beams of light follow geodesics. They are straight in the deeper geometry, but bent to our ordinary eyes. This leads to a subtle but profound shift. A straight line is not a rigid thing the universe must obey. It is always defined relative to the fabric it passes through. On a page of graph paper it is ruler straight. On a globe it curves along great circles. In space-time it bends with gravity. Straightness is not absolute. It is local, conditional, borrowed from the shape of the surface it rests upon. Think of a traveller walking across a landscape. To them, they are always walking straight ahead. But if you could step back and see the Earth as a whole, you would notice that their path curves following the planet's roundness. In the same way, we each live along what feels to us like a straight timeline, 1 second after another, moving forward with dependable rhythm. But from the perspective of physics, those paths are curved geodesics in the fabric of space-time, bent by motion and gravity. We are travellers convinced we walk straight, but the world beneath our feet is always rounding. It is easy to let the weight of such an idea feel intimidating, as if space-time curvature belongs only to equations scribbled in chalk. But listen for the gentleness in it. Space and time were once strangers. Einstein simply introduced them and showed that they were already in love. They moved together, inseparable, holding hands at every turn. Every moment of your life is a coordinate in this woven fabric, each heartbeat a dot along your geodesic. You're not floating in an empty stage, nor marching along an arrow of time alone, but riding the currents of a fabric that bends and sways, always carrying you along. As you rest tonight, perhaps with your body curved against a pillow, remember that space-time itself is a blanket too, stretched beneath you, carrying your weight, guiding the path of your every second. Straight lines may fill our notebooks and blueprints, but space-time refuses to flatten. It is curved, supple, elastic, and you are part of that curvature, woven into it with every breath. If space-time is a fabric, woven of where and when, then the threads that hold it together have their own rules. One of the most astonishing and perhaps most stubborn rules of this fabric is the speed of light. No matter who measures it, no matter how fast you're moving, no matter which direction you chase it from or which path you let it run away along, the result is the same: 300,000 kilometers every second, an unyielding pace. This number has become a kind of heartbeat of the universe. Everything else, planets, clocks, the way your thoughts tick, must bend to honour it. At first glance, it sounds almost impossible. Imagine a child running through a park holding a flashlight in front of them. If the child is running, say, 10 kilometers per hour, you would expect the beam of light to move a little faster relative to the ground than it would if they were standing still. This is the rule we follow with everything else. If you toss a ball forward while on a moving bicycle, the ball's speed is added to the bicycle's. If you row a boat down a river, the current lends you extra speed. That is how our everyday arithmetic works. Motion stacks, yet light refuses to stack. If the child points the flashlight while standing, the beam races ahead at light speed. If they sprint as fast as they can and point it again, the beam still races away at exactly the same pace. It does not matter whether you're strolling, sprinting, or travelling in a starship. The beam is loyal to itself, not to your speed. This strange loyalty puzzled scientists for decades, until Einstein folded it into his theory of relativity. To him, it was not that light was the strange one. It was that our ideas of time and space were too rigid. They would need to flex, like leather softening in the rain, in order to protect the constancy of light. If light insists on one unchanging speed, then space and time themselves must change shape to keep the promise intact. Let us take an image. Picture a concert hall where musicians are playing in perfect unison. The tempo of the music is fixed by the conductor's baton. Now imagine that the musicians begin to move around the hall, some walking slowly, some quickly. For each of them to keep the same tempo with the conductor, they may need to change the length of their steps or the timing of their movements. It is not that the music bends for them, but that they bend for the music. In the same way, the speed of light is the baton of the universe, and space and time alter themselves, stretching, contracting, slowing, quickening, so that the tempo never wavers. When something moves very fast, close to the speed of light, its space and time must give way. Lengths contract, meaning that distances in the direction of motion shrink. Time dilates, meaning that seconds themselves grow longer, ticking more slowly compared to someone who is standing still. To the traveller, life feels perfectly normal. Their seconds are still seconds, their heartbeat still beats in rhythm. But to an observer watching from the outside, the traveller's clock runs more slowly, their heartbeat lags, their journey through time takes a different pace. Think of it like this. You're looking through a window at a person walking along a treadmill. To them, each step feels the same as always. But if the treadmill itself were moving beneath your house, if the room itself were sliding while you looked, you might notice that their progress appears stretched or compressed, depending on the frame you use. They are not lying. Their steps are real. But the frame you choose changes what you see. In relativity, frames of reference are everything. Time itself is not absolute, but relative to how you move. Another way to picture it is with a candle. Imagine holding a lit candle in a darkened room. The flame flickers, and you count the seconds by each tremble of the light. Now imagine carrying that candle into a spaceship and accelerating near the speed of light. For you, the flame still flickers the same way, each tremble marking another second. But to someone watching from outside, peering through some impossible window, the flame seems to flicker more slowly, as if time itself has stretched. The candle has not changed. The rules of counting have. This might sound unsettling, as if our common experience of seconds and minutes is being stolen away by high speeds. But here is the gentleness in it. Your own experience of time never betrays you. If you are the one travelling quickly, you still feel the same stretch of a second, the same rhythm of your pulse, the same cadence of thought. Relativity does not rob you of your own time. It simply shows that different observers will measure it differently, because the universe has agreed to honour light above all else. We live our daily lives so far from light speed that we do not notice these changes. Cars and planes are too slow. Even the International Space Station is not nearly fast enough to make the seconds feel different. But in the mathematics of the cosmos, the rules are always in place, waiting. The faster you go, the slower your time flows, at least as measured by those who watch from outside your motion. A line that seemed straight in the old Newtonian view, time ticking evenly for all, no matter their speed, is now curved. Time bends with velocity, and the straight path is gone. And so, the speed of light is not just a number, it is a guardian. It ensures that cause precedes effect, that no traveller can outrun a message, that the structure of the universe is consistent. To maintain this guardianship, space and time must be willing to yield, to flex and give way. A straight timeline that was once thought absolute is no longer reliable. What endures instead is the curve, the bending of seconds and distances around that one unwavering constant. As you rest tonight, you can think of the light from your lamp or your phone screen. It leaves its source at that universal speed, the same whether you're still or walking or flying on a plane tomorrow. You and I and every atom are bound to adjust ourselves around it, stretching our experience so that light can keep its promise. In this way, the speed of light is not only a rule of physics, but also a quiet melody the cosmos hums to itself. And everything else, including time and space, dances in curved steps to keep in tune. When you first learn geometry as a child, it feels like one of the simplest and most certain languages the world has to offer. A line is the shortest distance between 2 points. A circle has a perfect roundness, and triangles behave exactly as they should, their angles adding neatly to 180 degrees. The paper on your desk, the blackboard at school, the chalk in your hand, these seem like the right stage for such shapes. Yet this comfort, while useful, is not the whole story. For the universe itself does not live on blackboards or sheets of paper, but on a stage that bends. Think for a moment of the globe, that familiar model of the Earth with its blue oceans and coloured continents. Take a piece of string and stretch it tightly across the surface from one city to another. On the globe, the string will curve, but if you lift that string off the globe and hold it in the air, it straightens instantly. Which view is true? Both, of course, because the definition of straight is not absolute. On the surface of the globe, the shortest path is not what you would call a straight line, but what mathematicians name a great circle. Airlines know this well. A flight from New York to London does not follow a flat ruler line on a map, but arcs over the Atlantic, following the gentle bend of the Earth. On a two-dimensional map, the path looks curved. On the globe, it is the straightest path available. This is the subtle trick the universe plays. It does not allow straightness to exist outside of the fabric on which it is drawn. What is straight on a flat piece of paper becomes curved on a sphere, and what feels straight in your everyday walk is curved in the geometry of space-time. We call these true straight lines geodesics. They are not arbitrary paths, but the ones that require the least resistance, the least effort. An object left to itself, an apple falling from a tree, a planet circling a star, even a beam of light racing through the darkness, will always follow a geodesic. Imagine yourself as a traveller walking forward across a vast rolling landscape. With each step you take, you insist to yourself that you're walking in a straight line. You keep your eyes on the horizon and your feet follow a steady direction. But if a bird could fly high above and look down, it would see that your path is bending along the contours of hills and valleys. The bird does not mock you for this. It is simply a reminder that straightness is a local experience, dependent on the surface beneath your feet. So it is with us. Each of us feels our life move forward in a straight line, second after second, but from the perspective of curved space-time, those lives are gentle arcs. The lesson can be both humbling and strangely comforting. On the one hand, it takes away the absolutes we once thought we possessed. The universe does not respect our ruler lines. It laughs gently at our perfect grids. Yet on the other hand, it means that we are always being carried along the simplest, most natural path possible. The geodesic is not a path we must constantly force ourselves onto. It is the path things take when they are free. Even the photons streaming from a star billions of light years away are simply following geodesics across the warped canvas of space-time. Their straight line is curved only because the canvas itself is curved. To hold this in your mind, picture a hammock swaying slightly between two trees. A marble rolled across the fabric will not travel in a rigid straightness, but along a dip, guided by the cloth beneath. You could scold the marble for failing to obey geometry, or you could recognise that it is simply honouring the fabric it rests upon. In the same way, the planets orbiting the Sun are not misbehaving by curving in ellipses. They are following the straightest possible path in a curved space-time. Their orbits are geodesics, the natural motion of bodies in the presence of mass. It is easy to forget how deeply this principle runs. Even light, that proud traveller, does not march unbent. When it passes near a massive star or a black hole, it curves. Astronomers have seen this again and again in the phenomenon known as gravitational lensing, where light from a distant galaxy is bent by an intervening cluster of matter, forming arcs and rings in the sky. To us, the beams of light seem to twist. But to the photons themselves, there is no twist at all. They are still moving in straight lines. Only those straight lines belong to a curved geometry. So when we say that the universe hates straight lines, we do not mean it acts with malice or disdain. We mean that in the presence of curvature, straightness is always something different from what we thought. A straight line is never absolute. It belongs to the surface on which it is drawn. Euclidean geometry, with its tidy triangles and parallel lines, belongs to flat paper. The universe, meanwhile, prefers Riemannian geometry, where surfaces can curve, parallel lines can meet, and triangles can have more or less than 180 degrees. This might sound like a betrayal of the lessons learned in school, but it is instead an expansion of them. Geometry has grown up just as we do, moving from rigid simplicity to the softer truth that things bend. As you lie quietly now, perhaps looking up at your ceiling, remember that even the ceiling is curving gently with the Earth, and the Earth is curving space-time around it, and space-time itself curves with the pull of galaxies. Straightness exists only in the smallest local sense, only where your ruler touches the paper or your foot touches the ground. Beyond that, everything bends, and in those bends, in those quiet arcs, the story of the cosmos is written. If you have ever been in a hurry, running to catch a bus or dashing across a street as the light changes, you know that the world feels different when you move quickly. The scenery blurs, your heartbeat drums in your ears, and the moments seem to stretch out strangely, as though your awareness is sharper, noticing details you would ignore when strolling. That sensation is not exactly the same as what physics describes, but it is a small echo of the truth. When you move faster, time itself does not behave as you expect. The faster you go, the slower your clock runs compared to someone who is standing still. This idea, time dilation by velocity, is one of the most famous features of Einstein's special relativity, and also one of the most difficult to accept because it contradicts our ordinary habits of thought. We are accustomed to believing that time ticks evenly for everyone, that a second here is a second there, that clocks are impartial machines and do not care how quickly you walk or run. Yet the universe is not so uniform. Motion bends the experience of time. To understand this gently, imagine that you are walking along a path covered with thick syrup. The faster you try to walk, the thicker the syrup seems to become. To you, moving at your chosen pace, every step feels natural. You do not notice the resistance, but to someone watching from outside, it appears as though you are moving more slowly than expected. In relativity, your own seconds are like those steps in syrup. You do not notice them stretching, but an outside observer sees your clock ticking more slowly the faster you travel. Another way to picture it is to think of your own heartbeat. At rest, your heart might beat 60 or 70 times a minute. If you sprint, your heartbeat rises, yet your sense of time does not seem to collapse. You still feel the seconds pass. But imagine if, by running fast enough, your heartbeat itself actually slowed down relative to others, so that while you felt normal, your friends waiting at the finish line counted fewer beats in the same span. That is what velocity does to time. Your body, your watch, your very processes of thought. Everything slows down relative to those who remain behind. Einstein expressed this with mathematics that can look forbidding, involving square roots and fractions, but the essence can be translated without symbols. As your speed increases toward the speed of light, the amount of stretching becomes larger and larger, until at the very limit, where no material object can actually reach, time for you would appear to stop altogether from the perspective of an outside observer. In practice, even at airplane speeds, the difference is tiny, a handful of nanoseconds. But at the velocities of subatomic particles, the effect is dramatic. Unstable particles that should disintegrate in less than a heartbeat instead live long enough to travel through detectors or even reach the ground from high in the atmosphere. Their clocks are running slowly because their speed bends time. Think of a cosmic ray particle born in the upper atmosphere, racing toward Earth at nearly the speed of light. To us standing on the ground, its life is stretched, extended beyond what we expect. To the particle itself, nothing strange occurs. It is still living through its brief natural span, but the rushing speed bends the measurement, allowing it to cover distances that should be impossible. Faster, and therefore slower. That is the paradoxical truth. We can also imagine two travellers, twins perhaps, as Einstein himself proposed in his famous thought experiment. One remains on Earth, growing older at the ordinary pace of days and years. The other climbs aboard a spaceship and races away near the speed of light, then returns. For the traveller, the journey felt natural, each day passing like any other. But upon return, the earthbound twin has aged far more. The rushing twin's clock, heartbeat, and very cells experience time more slowly relative to the sibling who stayed home. It is not a trick or an illusion. It is the bending of time by velocity. It is worth pausing to notice something subtle here. To the fast-moving traveller, there is no sensation of delay. Their seconds still feel like seconds. Their coffee still cools at the usual pace. Their heart still beats normally. Relativity never betrays you inside your own frame. The change appears only when you compare frames, when you step outside yourself and measure from another perspective. The straight line of universal time we once imagined has been replaced by many possible lines, each belonging to its own traveller, each tilted according to its speed. There is no single tempo that governs everyone. Instead, there is a dance of tempos, all consistent, all real, but none absolute. If this feels dizzying, let it also feel liberating. The universe is not rigid but supple. It allows time to be personal, local, dependent on how you move. Straight time for all was an illusion, convenient but not true. The deeper truth is curved. Motion bends the flow of seconds. So the phrase, faster means slower, is not a contradiction, but a quiet reminder of the universe's loyalty to light. To keep light speed constant for all observers, time and distance must yield. If you run fast enough, your time stretches. If you could fly near light speed, your years would dwindle, compared to those you left behind. In this way, the straight road of universal time has been replaced by curved paths, each shaped by motion. As you drift into rest tonight, perhaps think of your own heartbeat as a kind of clock, steady and unnoticed. Know that if you could ride a beam of starlight across the galaxy, your heart would still feel faithful to you. But to those watching from Earth, it would slow. Your seconds would widen, and your straight line through time would have become a long curve, bending toward eternity. Einstein often relied on imagination rather than elaborate laboratories, and in doing so he gave the world some of its most enduring pictures of how reality behaves. These are not the kind of thought experiments that require chalkboards covered in symbols. They're closer to stories, quiet daydreams about light and clocks and journeys. Tonight we will borrow two of the most famous, letting them unfold slowly, as if we were sitting together in an empty cafe late at night, stirring tea and considering what the universe might be like if we could ride alongside a beam of light. Begin with the image of a spaceship moving at a staggering velocity, say 90% of the speed of light. Imagine yourself standing inside it, holding a flashlight in your hand. You click it on, and a beam of light streams forward into the darkness. To you, standing there in the humming cabin, the beam moves ahead at the usual pace, 300,000 kilometers per second, just as it always does. Nothing in your experience suggests anything unusual, but now imagine a friend watching from Earth, peering through a telescope at your craft. From their perspective, you're already racing forward at an extraordinary speed. Intuition might whisper that your flashlight beam should be racing ahead even faster than normal, piling your velocity on top of the lights. Yet that is not what happens. To your friend's careful instruments, the beam of light also moves at the same speed, 300,000 kilometers per second, no more and no less. It does not matter that you are already in motion. The speed of light refuses to add up like ordinary things. It remains constant for you, for your friend, and for anyone else, no matter their perspective. This stubborn constancy forces the universe to adjust something else. If the light refuses to budge, then space and time themselves must bend in compensation. For your friend on Earth, watching you streak through the stars, your clock seems to tick more slowly. Each heartbeat of yours lags behind theirs. Your flashlight inside the ship still seems normal to you, but to the outside observer, time itself stretches in order to keep the speed of light steady. Distances, too, contract in the direction of your motion, so that the ship's length shrinks in their measurements. These distortions are not illusions. They are the fabric of reality reshaping itself to honour light's constancy. Now let us turn to another story, one that Einstein suggested to illustrate the strangeness of relative time. Imagine two siblings, twins who share everything from birthdays to family memories. One remains on Earth, living out a life of ordinary days, working, resting, watching seasons turn. The other climbs aboard a spacecraft and departs on a journey at nearly light speed. For the travelling twin, days and nights pass in their usual rhythm. They read books, sip coffee, gaze out at stars streaming past. Their body feels no difference, for their own seconds are unaltered in their frame. But when they return to Earth, stepping off the spacecraft with a smile, they discover something astonishing. Their twin who stayed behind has aged far more. Wrinkles have gathered, hair has greyed, decades may have passed. The traveller, by comparison, has lived only a fraction of that span. This is the famous twin paradox, though paradox is not quite the right word because the effect has a clear explanation. Time dilation depends on motion, and motion is relative, except when acceleration is involved. The twin on the ship experienced acceleration and deceleration during departure, turning around and return. These moments break the symmetry, making their frame of reference truly different from the sibling who stayed on Earth. The result is that the travelling twins' time stretched, flowed more slowly, allowing them to return younger than the one who never left. Though no human twin has yet undertaken such a journey, the principle has been confirmed in subtler ways. Particles in accelerators live longer at high speeds. Astronauts aboard orbiting stations experience slightly less aging than those on Earth, though the difference is minuscule, fractions of seconds, barely measurable. Yet the effect is real. Time bends for speed. To bring this down from the cosmic to the familiar, think of two friends agreeing to meet for tea. One walks steadily along the street, while the other detours by sprinting around the park before arriving. When they meet, both believe the same amount of time has passed. They feel their watches ticked evenly. But if the second friend had truly sprinted at near-light speeds, their watch would show fewer minutes. They would arrive younger than the one who strolled. In our ordinary world, the differences vanish in the noise of seconds, but at cosmic velocities the difference is no longer ignorable. This lesson carries a gentle irony. We often speak of speed as the way to shorten journeys, to arrive sooner. But in relativity, speed also shortens your experience of time itself. Travel fast enough, and journeys across the galaxy could be lived as brief adventures for you, while centuries might pass for those you left behind. Faster means slower. Your clock lags, your life stretches, even as distance shrinks before you. What does this tell us about straight lines? It tells us that the straight universal timeline we once assumed that everyone shares the same now cannot survive in the presence of such motion. Each traveller has their own tilted line through space-time, their own rhythm of seconds, their own story of aging. The lines diverge and reconverge, but never remain strictly parallel. Straightness gives way to a fan of possible paths, each curved by velocity. As you listen, perhaps lying comfortably with your eyes half closed, imagine the gentle light of that flashlight beam. It refuses to compromise, holding steady no matter who observes it. And so, to keep that promise, the universe bends time and space. Two twins part, and when they reunite, one has walked a longer arc through years, the other a shorter. Both are true, both are real, both are curved. Straight lines belong to our imagination. Motion has revealed a deeper geometry. If you were to ask a child what gravity is, they might hold out the hand, let a toy drop to the floor and say simply, "It's what pulls things down." That is how most of us first learn it, as an invisible tug pointing toward the ground. For centuries, that was the picture science used as well, a force acting across space, reaching out from the Earth to hold the moon, pulling the planets in their orbits around the sun. It was Isaac Newton who gave that tug its mathematical form, describing with extraordinary precision how apples fall and planets circle. His vision reigned for hundreds of years, reliable, useful, comforting in its clarity. Yet, like our rulers and grids, it was only part of the truth. Einstein replaced the tug with a bend. Gravity, he explained, is not a string pulling objects downward, but the natural effect of curvature in space-time itself. A planet does not need to be held in orbit by an invisible hand. It is simply moving along a geodesic, the straightest possible path, in a fabric that is curved by the sun's mass. The apple does not fall because it is pulled, but because the Earth beneath has curved space-time, and the apple, left to itself, follows the slope. The familiar tug is replaced by a gentler, stranger truth. Space and time themselves are shaped by matter, and the shapes they take guide everything that moves. To see this with your inner eye, imagine a wide bowl made of smooth glass. Place a marble at the rim and release it. The marble rolls inward, not because anything has tugged at it, but because the bowl slopes downward. The curve guides the path. Now picture space-time as that bowl, but spread in every direction, invisible and enormous. The Earth sits within that curvature, and you and I, along with every apple and every stone, are simply marbles rolling inward along its slope. It is not that we are pulled toward the Earth. We're following the slope of space-time carved by its mass. Now comes the part that makes gravity more than just a matter of orbits and falling. Because time is part of space-time, the bending of the fabric also bends time itself. The deeper you are inside a gravitational well, the slower your clock runs compared to one farther away. This is not just a poetic metaphor, but a measured reality. A clock at the bottom of a mountain ticks a little more slowly than a clock at the summit. An atom in a valley vibrates more slowly than an atom high in the sky. It is tempting to think of this slowing as if time was sticky, dragging in the depths, but perhaps a better image is of a flowing river. Imagine two leaves floating downstream. One glides along the surface of the river where the current is fast, while the other drifts lower in a region where the water moves more sluggishly. Both leaves feel they are moving naturally, yet from the perspective of the riverbank, the one nearer the bottom lags behind. Gravity reshapes the river of time in a similar way. The flow is gentler in the depths of a gravitational well, faster out in the emptiness of space. Astronauts and engineers have learned to respect this subtle slowing. When building the clocks that guide satellites and spacecraft, they must remember that time does not flow the same everywhere. Up in orbit, where Earth's gravity is weaker, clocks run faster than those on the ground. Deep within Earth's field, they run more slowly. The difference may be measured in microseconds each day, but that is enough to matter when you're navigating continents, timing radio signals, or guiding probes across the solar system. Gravity is not only the weight that holds our feet to the Earth, it is also the sculptor of time's rhythm. The effect becomes most dramatic near the densest objects in the cosmos. Around neutron stars and black holes, the slope of the space-time bowl is so steep that time itself seems to stretch almost to breaking. For an observer far away, clocks near such objects slow to a crawl. Light climbing out of the well loses energy, shifting to deeper colours, as though it had tired itself on the way up. To stand near the event horizon of a black hole, if that were possible, would be to experience seconds so different from the rest of the universe that your life would become incomprehensible to anyone outside. Yet for you, standing there, nothing would feel amiss. Your heart would beat, your thoughts would flow, your seconds would seem unchanged. Only the comparisons across distance reveal the bending. There is something quietly profound in this. It means that time, which we so often think of as universal, identical for everyone, is not absolute at all. It has texture, it has gradients, it has weight. You're living in a pocket of slowed time, tucked into the curvature created by Earth's mass. If you could rise high above the planet, floating where the pull weakens, your seconds would tick a little faster. Return to the surface, and they slow again. The very experience of now depends on how deep you sit in the well. So tonight, as you lie in bed, you are also lying inside a great slope in space-time. Your clock ticks, at a rate defined not only by its gears or circuits, but by your position in Earth's embrace. Each breath, each heartbeat, each passing second is part of a rhythm softened by gravity. You do not notice, for your whole body and mind are slowed equally. But compared to the vast spaces above, your time is different. The straight, even flow we imagine is once again revealed to be curved, shaped, and weighted. Gravity, then, is not simply a force that keeps your feet on the floor. It is the sculptor of the stage itself, shaping both your path through space and your passage through time. The marble in the bowl is not only rolling, its very ticking slows as it moves deeper. Straight time was always an illusion. Curved time is the reality we inhabit, whether we see it or not. If you step outside on a clear night and look up, you may notice not only stars but also points of light moving steadily across the sky. Some move swiftly, vanishing within minutes behind the horizon. Others crawl more slowly, appearing almost like stars that wander. These are satellites, silent machines circling above, unseen by most of us, except when their orbit and the sun's reflection let them sparkle briefly. There are thousands of them now, each tracing its own path through the heavens, each a part of our daily lives in ways we rarely think about. And among them, some of the most important are the satellites of the global positioning system, the quiet flock of machines that tell your phone where it is, guide airplanes, and allow ships to navigate oceans without sight of land. What makes them remarkable for our story tonight is not only that they orbit the Earth, but that they carry clocks. These are not ordinary clocks, but atomic ones, so precise that they can lose or gain only a fraction of a second over millions of years. They tick with the rhythm of atoms vibrating, faithful to a universal beat. Engineers designed them this way because the accuracy of your location depends entirely on the accuracy of their time. To know where you are, your phone listens to the signals from several satellites and measures how long those signals took to arrive. A difference of a millionth of a second in the ticking of one satellite can translate to hundreds of meters of error on the ground. In other words, without perfect time, the map in your hand would become useless. But here the universe plays its familiar trick. Those clocks in orbit do not tick at the same rate as clocks on the surface. They are affected by two competing distortions. First, because the satellites are moving quickly, their speed causes time dilation, slowing their clocks relative to those on Earth. Second, because they are high above the ground, where Earth's gravity is weaker, they experience less curvature of space-time, and that makes their clocks run faster than those on Earth. One effect slows them, the other hastens them, and together they do not cancel out. The net result is that the satellite clocks gain about 38 microseconds every day compared to clocks on the ground. That may sound trivial, but it is not. Left uncorrected, that tiny difference would cause your GPS location to drift by kilometers each day until your phone thought you were standing somewhere you had never been. To prevent this, engineers must program the satellites carefully, offsetting their clocks so that when both relativistic effects combine, the signals that reach Earth are in harmony with our time. The fact that this correction is not only considered but essential is one of the strongest proofs that relativity is not a lofty abstraction. It is a daily, practical necessity. Every time you open your map application, or every time a plane follows a navigation course across an ocean, it succeeds only because Einstein's insights about curved time and moving clocks are taken into account. Without them, the world would misplace itself. It is quietly astonishing to realise that the device in your pocket is in conversation with relativity. You may think you're just checking directions to a cafe or timing a run through the park, but your phone is measuring signals bent by the curvature of time itself. It is correcting for the slowing caused by speed, the hastening caused by altitude, and it is aligning your position to within a few meters by weaving together the fabric of space-time. Each time you see that little blue dot settle on your street, you're watching relativity at work. We live inside Earth's gravitational well, our seconds slowed just slightly by the planet's mass. We rarely notice because everything around us shares the same slowing. Your heartbeat, your thoughts, the clock on your kitchen wall, all are being drawn along at the same softened rhythm. But the satellites remind us that there is no universal tempo. Above the Earth, seconds tick differently. Out in deep space, far from any gravity, they tick differently again. Straight time is an illusion. Each pocket of the universe has its own flow, weighted by speed and by gravity. Think of Earth as a great hollow bowl carved into space-time, a depression in the fabric created by its mass. You and I are sitting deep inside it, at the bottom, our clocks running just a touch slower than those outside. The satellites, by contrast, circle higher up the slope of that bowl, where the curve is gentler. Their clocks, therefore, run faster. And so, we must adjust, reconciling two perspectives into one agreement. We are like musicians playing from different sections of an orchestra, each with a slightly different sheet of music, yet forced to harmonise. Relativity is the conductor, ensuring the notes align. This harmony is not only practical, but also philosophical. It means that time is not an independent stage upon which we act. The same for all observers, steady and impartial. Instead, time is deeply entangled with where you are and how you move. We live within Earth's pocket of slowed seconds, and we design technology that can peak beyond, reaching into faster or slower flows to keep our maps coherent. The thought may feel dizzying, but it is also grounding. It means that your now is not the universe's now, but a particular note struck by your position on the slope of space-time. As you rest tonight, perhaps with your phone beside you on the table, remember that even in sleep, those satellites continue to orbit, their clocks singing against ours, their signals adjusted so that the world makes sense in the morning. The fact that you can wake, open your map, and see yourself precisely placed is a quiet triumph of human ingenuity and cosmic law. Beneath the convenience of navigation lies the profound truth that time itself bends. You're cradled in Earth's gravitational well, moving through seconds that are heavier than those above. The satellites dance around the rim, their clocks lighter, faster, yet tuned to match. And together, this orchestra of bent time plays the melody of your location, one soft correction at a time. The universe has many ways of whispering its secrets, but one of the clearest is through the ticking of clocks. If relativity were merely a clever idea drawn on paper, we could smile at its elegance and move on. But the truth is that it has been tested again and again by experiments that take place not in distant galaxies, but here on Earth, with instruments we can hold and particles we can measure. To see time bend is no longer a matter of imagination. It is a matter of evidence. One of the most famous demonstrations came in the 1970s, when a team of physicists decided to carry atomic clocks aboard commercial airplanes. These clocks were marvels of precision, far more reliable than anything mechanical, and they could register differences of billionths of a second. The experiment was simple in design but daring in implication. Fly the clocks eastward around the world, then westward, and compare them with clocks that had remained behind at the US Naval Observatory. According to relativity, the moving clock should not keep perfect step with the stationary ones, and when the planes landed, that is exactly what was found. The eastward clocks lagged, the westward clocks gained, and the clocks on the ground held their own rhythm. The differences were small, measured in nanoseconds, but they were undeniable. The Earth itself had become a laboratory, and time had revealed its pliability. You can picture the scene if you like. A plane gliding high above the Atlantic, passengers dozing in their seats, unaware that in the cargo hold, inside a secure container, a clock is quietly living a different life. Each tick inside the case is a fraction slower or faster than its siblings on the ground. When the plane touches down and the instruments are reunited, the comparison is like greeting an old friend and noticing a subtle change. A slightly different pace in their footsteps, a mere rhythm just out of sync. The difference is not an illusion of measurement. It is reality, curved by speed and gravity, recorded in the very heartbeats of atoms. The skies are not the only place where this bending shows itself. High above the Earth, the atmosphere is constantly bombarded by cosmic rays, energetic particles streaming from distant space. When these rays strike molecules in the upper air, they create showers of secondary particles, including unstable ones called muons. A muon's natural lifetime is so short, about 2/millionths of a second, that, travelling at near light speeds, it should decay long before reaching the ground. By ordinary arithmetic, not a single muon should make it to sea level. And yet, When physicists set up detectors at the surface, they find muons in abundance. How is this possible? The answer is time dilation. From our perspective on the ground, the muons are moving so fast that their internal clocks run more slowly. What feels like 2/millionths of a second to them stretches into far longer from our point of view, enough to allow them to travel kilometres through the atmosphere before decaying. To the moons themselves, nothing unusual is happening. They are simply living their natural lifespans, 2/millionths of a second as always. But to us, they are gifted with an extension, a grace period borrowed from the curvature of time. Every muon that taps a detector at the surface is a messenger from relativity, proof that faster means slower, that seconds stretch when velocity climbs. Accelerator laboratories provide another stage for the same drama. There, particles are whipped around circular tracks at speeds just shy of light, nudged by magnets and guided by beams. These particles too are unstable, their lives measured in fleeting instants. But inside the accelerators, their lifetimes stretch dramatically. They circle the ring thousands, millions of times before decaying, far longer than they should by Newtonian reckoning. The machines themselves are not protecting them. It is time, bent by velocity, that allows them to endure. In a sense, these accelerators are clocks themselves, showing us that relativity is not a curiosity but a daily participant in science. Imagine standing by such an accelerator, the ring hidden beneath layers of concrete, the hum of machinery in the air. Deep inside, invisible to your eyes, particles race faster than you could ever dream of running. Each one carries its own clock, ticking faithfully, but those ticks are stretched, slowed, softened by their speed. The effect is not something the particles negotiate or decide. It is written into the structure of reality. Their lifetimes lengthen not because of any gift, but because motion bends time itself. From airplanes carrying clocks to the skies filled with muons to the accelerators humming in their underground halls, the evidence gathers. Relativity is not a theory awaiting proof. It is a truth we meet every day, if only we know where to look. These experiments do more than verify Einstein's predictions. They reveal that straight universal time is gone, replaced by curved time, personal time, woven into the motions of each traveller. As you think about this, perhaps lying back with your eyes heavy, remember that the very particles passing through you at this moment may be living longer than they should, their tiny clocks slowed by their speed. The air is full of these fleeting guests, cosmic visitors whose presence is a constant demonstration of relativity. Even as you rest, the world is an experiment, every tick of every clock confirming that time bends. It is one thing to hear that clocks flown on airplanes tick differently, or that particles in accelerators live longer, but it is another thing to realise that the same bending of time shapes your daily life in ways you may never notice. Relativity is not only a chapter in a physics book, or an experiment performed by specialists in lab coats. It has become part of the invisible machinery of modern life, so woven into our habits that you can benefit from it while sitting at a cafe, phone in hand, unaware that your map is whispering in Einstein's language. Consider again the global positioning system, that silent flock of satellites circling above us. Without relativity, it would fail within hours. Every day, each satellite's clock drifts by a few dozen microseconds compared to clocks on Earth. A few dozen microseconds might sound like nothing, but because signals travel at the speed of light, every microsecond of error translates to hundreds of meters of positional inaccuracy. Within a single day, your location could be off by kilometers, placing you in the middle of a river when you're standing on a sidewalk, or in another neighborhood entirely. The corrections that keep the blue dot steady on your phone are corrections to time itself, compensations for both the speed of the satellites and their height above Earth's gravity. Your daily commute, your ability to find a cafe tucked down a side street, even a plane navigating over an ocean, none of these would be possible without relativity humming in the background. Relativity follows us into the skies in other ways. Airline pilots, astronauts, Even high-altitude mountaineers experience tiny but measurable differences in aging compared to those who remain at sea level. For astronauts aboard the International Space Station, orbiting at more than 7 kilometers per second, the twin distortions of motion and gravity balance in a delicate dance. Their speed slows their clocks, while their altitude farther from Earth's centre speeds them up. The result is that after months in orbit, an astronaut returns very slightly younger than if they had stayed on Earth. The difference is measured in milliseconds, not decades, but the principle is real. Their life's arc has curved differently, simply because they were moving faster and sitting higher in the gravitational well. They may laugh about it, joking that space travel is the secret to staying young, but in those milliseconds lies proof that time itself is personal. Even your electronics, those silent companions on desks and in pockets, must reckon with relativity. Modern electronics operate on timescales so fine that the difference between 1 nanosecond and the next matters. Engineers who design microchips must know that signals moving through circuits are bounded by the speed of light, and that synchronization of distant systems requires relativistic adjustments. The very internet, carrying voices and messages across the globe, is kept coherent because satellites and fibre optic lines are calibrated with Einstein's corrections in mind. If they were not, information would wander, clocks would fall out of step, and the quiet symphony of global communication would begin to lose its rhythm. Hospitals, too, quietly acknowledge relativity. Particle beams used in cancer treatments, accelerated to high speeds, are guided by calculations that include the stretching of time and the contraction of lengths. Doctors may not speak in the language of geodesics, but the machines that save lives rely on them. In this sense, relativity is present not only in the maps on your phone or the experiments of scientists, but also in the healing of bodies, the beating of hearts, the continued lives of those who might otherwise have lost their time entirely. If this all seems surprising, it may be because relativity often carries the aura of science fiction. We hear of travellers near black holes, of voyages where decades pass on Earth but only hours for the crew, of cosmic horizons where time stands still. Those are dramatic and real consequences of the theory, but the quieter truth is that relativity is as close as your morning walk, your phone in your pocket, the satellites circling above, and the beams humming in hospital basements. Science fiction has become domestic, woven into the background of the ordinary. Think of yourself sitting in a chair, the clock on the wall ticking away, the world outside seeming stable. Yet above you, satellites circle and adjust their clocks. In laboratories, particles race around accelerators, living longer lives than expected. In hospitals, machines guide beams along curves defined by relativity. Without any effort on your part, you're immersed in a world whose coherence depends on these curved laws. You may never feel the bending directly, but its fingerprints are everywhere. Perhaps this is the quietest lesson relativity teaches. Straight time, the idea that seconds tick the same for all, was once taken for granted. Now we know that each observer carries their own clock. Each path through space-time has its own rhythm. The satellites orbiting above, the astronauts circling Earth, the pilots flying over oceans, the patients treated by particle beams, all of them are living slightly different tempos of time. And yet, in order to make sense of our world, we have learned how to stitch those tempos together, to correct and synchronize, to build technology that harmonizes differences into something coherent. Relativity is not only a theory of curvature, but also a lesson in cooperation. Many times, many rhythms, all reconciled into one usable whole. So the next time you glance at the blue dot on your phone, remember that it is not merely a calculation of distance. It is a conversation with the bending of time, a dialogue between satellites and ground, a correction for the fact that speed and gravity refuse to let seconds march straight. That quiet convenience is built on cosmic strangeness. And as you drift toward rest tonight, you can think of it as proof that even in our daily routines, even in the smallest details, the universe's dislike for straightness is always with us. If there is one pattern that seems to have captured the universe's imagination, it is the spiral. Look closely at the small, at the shells scattered along a beach, and you will see it. Look at the vast, at galaxies wheeling across the darkness, and you will see it again. The spiral is a curve that repeats itself at every scale, as if the universe enjoys sketching the same graceful gesture again and again, from grains of sand to clusters of stars. Begin with the seashell, lying quietly where the tide has left it. Its curve is not random but follows a particular rhythm of growth, what mathematicians describe as logarithmic spiral. As the creature inside grows, it adds to the shell in a way that preserves its shape. Each new chamber is proportionally larger, but the spiral remains the same. To our eyes, it is pleasing because it seems balanced, not widening too quickly, not tightening too sharply, just unfurling steadily, like a ribbon laid down in slow motion. Children instinctively hold shells to their ears, listening for the ocean inside, as if the spiral could hold not only shape but memory. Move outward to the weather above the ocean. When storms gather, air and water swirl together, and the same spiral emerges. Hurricanes, cyclones, even the simple curl of steam rising from a hot cup of tea, all arrange themselves in curves. The physics behind it is complex, involving pressure and rotation, but the result is simple to see. The air prefers to spin into spirals. There is efficiency in it. A spiral distributes energy smoothly, allowing the storm to sustain itself, just as the seashell grows by repeating its form. In both, there is a sense that the spiral is the path of least resistance, the natural way for things to expand or rotate. Then lift your gaze beyond Earth entirely. Galaxies, those great gatherings of hundreds of billions of stars, often arrange themselves in spirals. From the side, a spiral galaxy looks like a thin disk, but from above, its arms extend outward in sweeping curves, each arm a stream of stars, gas and dust slowly winding around the centre. These arms are not solid structures. They are more like traffic patterns on a cosmic highway, regions where stars cluster as waves move through the galactic disk. But to our eyes, they form graceful swirls of light. To look at a photograph of the Andromeda Galaxy or our own Milky Way is to be reminded of the same form found in shells and storms. The universe seems to be echoing itself, drawing the spiral at scales so different they defy direct comparison, yet still recognizable. Why spirals? One answer is efficiency. In growth, the logarithmic spiral allows expansion without distortion. In storms, the spiral organizes motion so that forces balance. In galaxies, the spiral emerges from gravity and motion distributing matter across space. Another answer is beauty. Though the universe does not plan for our aesthetic tastes, the fact that spirals feel beautiful to us may not be coincidence. We are part of this same universe, shaped by its patterns, and our sense of harmony may be a recognition of the forms that nurture life. Plants arrange their leaves in spirals to maximize sunlight. Pine cones and sunflowers arrange seeds in spiral patterns that match the Fibonacci sequence, packing them efficiently. The spiral is not only beautiful, it is practical, sustaining, and everywhere. Think of the spiral staircase, that human imitation of the curve. Walking one, you rise steadily without climbing too steeply. Each step carries you forward and upward in balance. The seashell, the storm, the galaxy, the sunflower, they all walk their own spiral staircases, rising or expanding without strain. Straight lines would be brittle, prone to breaking or failing to adapt. Spirals bend, and in their bending, they endure. It is tempting to think of the spiral as a kind of secret signature of the cosmos, hidden in plain sight. When you next slice open a red cabbage and see the coils within, or notice the curl of smoke from a candle, or gaze at an image of a galaxy millions of light years away, remember that you are seeing the same gesture repeated. The scale changes, but the handwriting is the same. The curve repeats itself across scales. There is something soothing in this, especially as you listen now, perhaps with your thoughts curling into sleep. It suggests that the universe is not chaotic but rhythmic. Patterns reappear, not because of coincidence, but because they are the most natural way for matter and energy to arrange themselves. If the straight line is our attempt at control, the spiral is the universe's way of saying, this is how things truly grow. So tonight, when you close your eyes, imagine yourself standing in the centre of a vast spiral, its arms reaching outward, wrapping around you in gentle curves. You might think of it as the swirl of the Milky Way, or the unfolding of a shell, or even the pattern of air curling in the room as you breathe. In that spiral, you are held by the same logic that guides storms and galaxies. Straightness is absent here, but order remains, an order written in curves. If spirals are one of the universe's favourite gestures, then branching is another, just as common, just as deeply inscribed into the patterns of life and matter. Branches appear whenever something needs to spread, to divide, to reach outward across distance. They're not random. They follow subtle logics of efficiency, of distributing flow, of making the most of what is available. From rivers carving valleys to trees unfolding leaves to the delicate bronchi inside your lungs, branching is everywhere. A natural refusal of straightness in favour of multiplication and spread. Consider first the great rivers of the world seen from far above. From a plane window or a satellite image, a river is never a single line. It gathers streams into tributaries, then splits again into smaller channels, weaving a pattern that resembles veins in a leaf. Straight rivers exist only in maps tamed by human hands. In reality, the flow bends and curves, meanders and divides. This is not inefficiency. It is how water distributes its energy, spreading across a floodplain, carrying nutrients, softening the land. Look at the delta of the Nile, the Mississippi or the Ganges, and you will see fingers of water reaching toward the sea, not one arrow but many branching into a fan. The straight channel is rare, fragile and temporary. The branching flow is strong and lasting. Now shift your gaze upward to the trees that line those riverbanks. Their shapes mirror the waters that nourish them. From the trunk rises a split, then another, then countless more, until leaves spread wide, each supported by its own tiny twig. The pattern is recursive, repeating itself at smaller and smaller scales. A tree is not designed on graph paper, but grown through division, each new branch forming where light and air and space invite it. If a tree tried to grow in a straight column without branching, it would offer no canopy, no leaves to catch the sun. Branching is how it breathes, how it drinks light, how it survives. And so the forest becomes a collection of branching networks, each tree an echo of rivers, each branch a flowing curve. The resemblance between rivers and trees is not coincidence. Both are solving the same problem: how to distribute resources efficiently. Water must flow across land, light must reach leaves, nutrients must spread through veins. Branching achieves this by multiplying paths, each smaller than the last but all connected. The same solution appears inside your own body. Look within, and you will find that your lungs are forests. The air you breathe travels down a single windpipe, then divides into bronchi, then into smaller bronchioles, and finally into tiny alveoli, millions of microscopic sacs where oxygen and carbon dioxide exchange. If your lungs were laid flat, their surface area would cover a tennis court. They achieve this vastness not by being large and straight, but by branching endlessly, turning limited space into infinite pathways. Each breath is a testimony to branching, each sigh a reminder that straightness would not sustain life. Lightning, too, honours this pattern. When a storm builds and the air becomes charged, a bolt of lightning searches its way downward, not as a single straight strike, but as a fractal cascade. The current divides, forks, branches, finding the easiest path through the air's resistance. Photographs of lightning capture these sudden, brilliant veins of light, spreading like the roots of a glowing tree. The branches may appear random, but they follow hidden logics of resistance and charge. In their spreading, they maximize the chance of reaching the ground, of releasing energy where it can. The jagged path is not a flaw. It is the natural language of electricity in a medium that resists it. Fractals, the mathematics of self-similarity, give us another way to understand this. Coastlines, for example, appear simple on a map, a line between sea and land. But walk along one and you see bays and peninsulas, then smaller inlets, then pebbles and grains, each repeating the same roughness. The more closely you look, the more detail appears. Straightness vanishes under magnification. Complexity replaces it. This is what makes fractals so powerful. They reveal that nature's patterns repeat across scales, whether in branches of rivers, veins in leaves, or bolts of lightning. To imagine this softly, picture holding a piece of broccoli in your hand, perhaps the Romanesco variety with its beautiful green cones spiralling into smaller and smaller versions of themselves. Each floret resembles the whole. The structure repeats, not perfectly but recognisably. This is what rivers and trees and lungs are doing, though we rarely notice it. Straight lines could never achieve such efficient complexity. Branching, fractal, self-similar curves make the most of limited space. Why does the universe prefer this? Because flow is rarely served by rigidity. Water, light, air, electricity, blood, all of them must move, and they move best when spread. Straight pipes or channels force energy into narrow paths, making them brittle. Branches distribute, absorb, soften and adapt. That is why rivers meander, why trees spread, why lungs divide, why lightning forks. Straightness fails, branching endures. As you lie here listening quietly, you're surrounded by branching patterns. The veins under your skin carry blood in fractal paths. The streets of your city from above look like branches dividing and dividing again. The very neurons firing in your brain are branching trees, sending signals across their synapses in fractal webs. You're a collection of branches inside a collection of branches, part of a universe that distributes itself not in rigid lines but in networks. And so, once more, we see that the straight line belongs to us, to our maps, to our attempts to simplify. The universe itself chooses branches, fractals, flows. It multiplies paths rather than forcing one. It curves rather than insisting on rigid alignment. To live is to branch. To breathe is to branch. To think is to branch. Straightness cannot sustain. Curves and divisions are the true shape of life. When we picture the universe, we often imagine it as a vast scattering of stars, as though someone had taken a handful of glitter and tossed it across a black canvas. To our naked eyes on a clear night, the stars do appear sprinkled at random, points of light shining wherever they happen to land. Yet if we lift our perspective far beyond what eyes alone can see, beyond even the reach of most telescopes until the canvas becomes a map of billions of galaxies, the pattern changes, the scatter reveals structure. Galaxies are not scattered like random sparks. They are gathered, connected, arranged into something more intricate. At the grandest scales, the universe resembles lace. Astronomers call this the cosmic web. It is a network of filaments, long, thin threads of galaxies stretching for hundreds of millions of light years. Along these threads, matter clusters into knots where filaments intersect, forming dense regions that we call galaxy clusters. Between the filaments lie enormous empty expanses known as voids, regions so vast and dark that they can span hundreds of millions of light years, with barely a handful of galaxies inside. The result, when seen in computer simulations or deep surveys, looks astonishingly like a piece of delicate lace draped across space. Threads, nodes, and holes, forming a repeating pattern of connection and emptiness. It is worth pausing to notice how little this resembles the grids and straight lines we often imagine. There is no cosmic checkerboard, no neat arrangement of galaxies in squares. Instead, the web is organic, almost biological in its appearance, like the filaments of a neuron under a microscope or the delicate threads of mycelium spreading through soil. The universe, in its largest architecture, refuses our tidy lines and builds instead a network of curves. To understand how such a lace could form, imagine the universe in its earliest moments, filled with a nearly uniform mist of matter and energy. That mist was not perfectly smooth. Tiny fluctuations, some regions just slightly denser than others, were present. Gravity with its patient hand pulled matter toward those denser spots, and over billions of years, those small differences grew into vast structures. The denser regions became filaments, pulling in matter from their surroundings, while the emptier regions grew emptier still, creating the voids. The result is the lace we see today, a tapestry woven from the earliest whispers of imperfection. This lace is not only beautiful, it is practical. Along the filaments galaxies form and evolve, star formation flourishes, and heavy elements are forged. In the voids, silence reigns. If you could somehow float in the centre of one of those immense dark regions, you would see almost nothing in any direction, an emptiness that would dwarf your imagination. Yet travel outward to the filaments and you would find the universe bustling with light, stars packed along cosmic highways of matter. Life as we know it is possible only because the web exists. Without it, the universe might have remained a bland, featureless mist, with no galaxies, no stars, no planets, no eyes to look back upon it. To hold this image gently, picture a spider's web shimmering with dew at dawn. The threads glisten, each drop reflecting light, while the spaces between stretch wide and empty. Now imagine that web not stretched across a garden, but across the whole of the universe, and instead of drops of dew, imagine galaxies, each containing billions of stars. That is the cosmic web. You live inside one of its filaments, in a galaxy we call the Milky Way, itself just a drop of light clinging to the threads. Straight lines vanish at these scales. The universe does not lay galaxies in parallel rows or geometric lattices. It weaves them, stitches them into filaments and knots. Even emptiness becomes part of the design. The voids are not errors or gaps. They are spaces that allow the threads to be seen more clearly, the black background against which the lace pattern shines. There is a quiet poetry in this arrangement. Human beings often imagine that order requires straightness, that the neatest plan is the most efficient. Yet the cosmos tells another story. Its greatest architecture, spanning billions of light years, is a pattern of curves and gaps, of threads and holes. It is more like a woven cloth than a rigid grid, more like a living organism than a machine. The straight line has no role here. The arcs and filaments carry the weight of creation. As you rest tonight, you can imagine yourself as a single bead on that lace, your life unfolding on a planet orbiting a star tucked into one arm of a galaxy that lies within a filament. Around you stretches a universe not of straight lines, but of threads, each connected in ways both visible and invisible. The emptiness of the voids may seem haunting, but they are also part of the design, the spaces that let the lace breathe. You are not lost in randomness. You are cradled in a pattern that spans the cosmos. And so, once again, the universe shows its preference. It does not draw grids, it weaves webs. It does not march in straight lines. It loops, curves, knots, and spreads. To see the cosmic web is to see that preference made grand, to see that straightness is not the skeleton of the cosmos. The skeleton is lace. If you wish to see the universe's dislike of straightness taken to its most dramatic form, you need only look toward a black hole. These are not merely objects, but regions where space-time itself has curved so intensely that no path can lead outward once crossed. They are the final punctuation marks of collapsed stars, the densest knots in the cosmic lace, places where even light, that swiftest traveller, finds no escape. Yet as strange and fearsome as they sound, black holes are also teachers. They reveal in stark clarity that time and space do not flow straight, but bend, twist, and sometimes nearly break. Imagine a traveller approaching such a black hole. To them, nothing feels unusual at first. They may drift past orbiting stars, glide through fields of dust, and feel the pull grow stronger as they near the horizon, but as long as they remain outside, life continues as always. Their heart beats, their watch ticks, their thoughts proceed in ordinary rhythm. If they are brave or reckless, they may decide to fall inward. From their perspective, crossing the event horizon, the invisible boundary of no return is uneventful. No alarms sound, no lights flash. They drift past as if through an invisible curtain, continuing on their path inward. Their seconds are still their seconds, flowing smoothly. Now shift your view to a distant observer, watching through a telescope from far away. To that watcher, the traveller's fall slows more and more as they approach the horizon. The seconds stretch, the movements lag, the signals arriving from their clock begin to appear delayed. From this perspective, the traveller never quite crosses the horizon at all. They seem frozen, suspended at the edge of darkness, fading gradually as their light grows weaker and redder, stretched by the gravitational pull. To the outside world, the fall becomes endless. To the falling traveller, it continues unbroken. Both perspectives are true. This double story is one of the great paradoxes of black holes, though paradox here does not mean contradiction. It means that the universe allows two accounts to be simultaneously correct, each belonging to its own frame of reference. To the traveller, time is local, smooth, straight in its own way, carrying them inevitably deeper. To the observer outside, time is curved nearly flat at the horizon, stretched to infinity, freezing the motion. Each frame writes its own version of events, and both are written in the geometry of space-time. To hold this gently in the mind, imagine watching a snowflake fall toward a river. From where you stand on the bank, the flake drifts downward, but then a patch of fog thickens above the water. To your eyes, it looks as if the flake has paused at the edge of the mist, no longer moving, its descent slowed to nothing. Yet if you could slip into the fog yourself, you would see the flake continuing to fall, entering the mist and vanishing beneath the surface. Both stories are consistent. The stillness from outside, the motion from within. A black hole is that fog made permanent, a curtain drawn across reality. What does this tell us about straightness? It shows us that even the most basic expectation, the idea that an object moves forward in time in the same way for everyone, cannot survive in curved space-time. Straight time, for all observers, does not exist here. Instead, time bends differently for each perspective. The same fall is both frozen and flowing, both halted and continuous, depending on where you stand. Scientists measure this bending not only in thought experiments, but in the signals of real black holes. Light from matter falling inward stretches and reddens, just as the distant observer would predict. The outside world never sees anything cross the horizon, only the fading glow of matter slowed into silence. In a sense, the horizon is like a cosmic museum exhibit, where falling things are displayed forever at the edge, never quite vanishing from view. Yet for the matter itself, there is no museum, no pause, no delay. It falls, it crosses, it continues into the depths. And what lies within? That's a question still wrapped in mystery. General relativity tells us that matter collapses to a singularity, a point of infinite density, where space-time curves beyond comprehension. Quantum mechanics whispers that such infinities cannot exist, that something more subtle must take their place. But whatever the answer, the lesson remains. The straight lines we once imagined for time and motion do not apply here. Near a black hole, even the act of falling is a story told in two voices, each curved, each true. As you let this settle in your thoughts, you might imagine lying beneath a night sky and seeing not only stars but also places where no light returns, dark patches against the glitter. Somewhere out there, perhaps in the heart of a galaxy, matter is falling into such darkness. To those objects, their fall is natural, seconds flowing as always. To us, watching from afar, the fall slows, freezes, stretches into eternity. In that difference lies the curve of time, bent by gravity until straightness dissolves. So when you hear of black holes, do not think only of destruction or fear. Think also of their quiet lesson. They show us that there is no single account of time, no single straight story. There are many, each curved by perspective, each woven into the fabric of space-time. In their silence, in their darkness, they reveal the universe's dislike of straight lines more clearly than almost anything else. If black holes are the universe's most dramatic refusal of straightness, then neutron stars are perhaps its most haunting compromise, poised just before the threshold where space-time caves in completely. They are the remnants of massive stars that have burned through their fuel, collapsed inward, and stopped just short of becoming black holes. What remains is an object only a few kilometres across, yet so dense that a single teaspoon of its matter would outweigh a mountain. These stars are paradoxes of scale, tiny compared to their former selves, yet carrying more mass than the sun inside a sphere small enough to fit within a city. In such places, gravity bends not only space, but time to an extraordinary degree. Imagine standing on the surface of a neutron star, if that were even possible, which it is not, for no human body could survive the crushing gravity. From that vantage, every second would pass more slowly than it does here on Earth. Your heartbeat, if it could somehow continue, would lag behind the rhythm of hearts back home. Your watch would tick, but its hands would fall behind the same watch kept safely on Earth. Time itself is stretched by the sheer density of matter. To you, of course, nothing would feel different. Seconds would still feel like seconds. But to an observer watching from afar, your life would seem slowed, as though the star's gravity had pressed its thumb against the flow of time. Astronomers do not have to imagine this. They can see it written in the light. Neutron stars often emit powerful radiation, including X-rays. When these photons struggle upward through the star's enormous gravity, they lose energy, shifting to lower frequencies. To us, the light appears stretched, redder, less energetic than when it began. This effect is called gravitational redshift, and it is a direct sign that time is flowing differently at the star's surface. The ticking of atomic vibrations, the oscillations of particles, the very heartbeat of the star, all are slowed by the immense weight of its gravity. Observing these shifts is like eavesdropping on the star's internal clock, hearing it run in a rhythm different from our own. The density of neutron stars gives them other remarkable qualities. Many spin rapidly, completing a full rotation dozens or even hundreds of times each second. Their magnetic fields are immense, guiding streams of radiation that sweep across the cosmos like lighthouse beams. When one of these beams happens to cross Earth, we detect it as a regular pulse of radio waves or X-rays, so steady that these objects are called pulsars. For a time after their discovery, the pulses were so regular that some wondered if they might be signals from distant civilizations. But the truth is even more humbling. They are the sound of dense matter's heart, ticking in a slowed rhythm, carried across the universe. To imagine a pulsar gently, think of a lighthouse on a stormy coast. Its beam turns again and again, casting light across the waves. From a ship at sea, each flash is a heartbeat of safety, a reminder of land nearby. In the same way, the pulses of a neutron star travel across the dark ocean of space, steady, unwavering, marking time not in seconds but in the slowed cadence of curved space-time. Each flash is both a light and a clock, telling us that even here, at the brink of collapse, the universe continues its pattern. no straight flow of time, but a curved and weighted rhythm. It is worth reflecting on how close these stars come to becoming black holes. If a neutron star gathers too much additional mass, perhaps by merging with a companion, it can collapse further and vanish into a horizon. At that point, the compromise is broken, and space-time curves so steeply that not even light can escape. But as long as they remain just shy of that fate, neutron stars show us the borderland. They are reminders that even before the final collapse, time already bends nearly to breaking. We, on Earth, live in a gentle gravitational well. Our seconds are slowed compared to deep space, but only slightly. The dilation is measurable only with sensitive instruments. But near a neutron star, the slowing is profound. It tells us that time is not something abstract or universal, but a local property, tied to the weight of matter nearby. A clock on Earth runs differently from one in orbit, and a clock on a neutron star would run differently still. Straight universal time does not exist. Time is curved, pressed, stretched, and delayed by matter. If you close your eyes now and listen for a sound in your imagination, you might hear the steady beat of a pulsar. Each tick is a note in the universe's deeper symphony. Each one is a reminder that clocks are not independent of place, that even the vibration of atoms yields to gravity. Neutron stars are extreme, but their lesson echoes here as well. Time bends wherever matter gathers. So the next time you see an image of a lighthouse or hear the ticking of a clock, you can think of those distant stars, compressed into unimaginable density, pulsing across the cosmos. Their beams are the slowed heartbeat of matter at its brink. They are proof that the universe, even when it seems harsh and violent, is still consistent in its refusal of straightness. Time does not march evenly. It curves, it falters, it lingers, especially in the presence of extraordinary weight. If you have ever tossed a stone into a quiet pond, you know what follows. From the point of impact, circles spread outward, gentle waves moving across the surface. They ripple past lily pads, bend around reeds, and eventually fade into the distance. Water carries the disturbance, allowing the memory of that single splash to travel far beyond its origin. Now, imagine that the universe itself is capable of rippling in the same way, not just through matter, but through the very fabric of space and time. These are gravitational waves, the soft undulations of space-time itself, set in motion by some of the most violent events the cosmos can host. For a long time, they were only predictions. Einstein's equations hinted at them over a century ago. Disturbances in space-time created when massive objects accelerate, travelling outward at the speed of light. But they were thought to be impossibly small, too delicate to detect. Space-time is stiff, and its ripples barely shift even the finest instruments. For decades, gravitational waves remained in the realm of theory, a whisper no one could quite hear. And yet physicists persisted. They built instruments of astonishing delicacy, hoping to catch the faintest tremor. The most famous of these is LIGO, the Laser Interferometer, gravitational wave observatory, spread across 2 sites in the United States. Each site holds 2 long tunnels, 4 kilometers in length, set at right angles. Within them, lasers bounce between mirrors with exquisite precision. If a gravitational wave passes through, it stretches one arm of the instrument while compressing the other, by a distance smaller than the width of a proton. By comparing the light's path in each arm, scientists hope to see that tiny stretching. Imagine the challenge of listening for a ripple smaller than an atom in a world filled with earthquakes, passing trucks, and even the footsteps of birds. For years, LIGO listened, hearing only noise, refining its instruments, waiting patiently. Then, in September of 2015, the whisper finally arrived. 2 black holes, each more massive than the Sun, had collided over 1 billion light-years away. Their spiralling dance churned space-time, sending out waves that spread across the cosmos. When those waves reached Earth, LIGO's detectors stirred. The signal was short, less than a second, but it was unmistakable. A rising tone as the black holes drew together, merging into one. That sound, because the signal was converted into audio, was not dramatic, not the roar of thunder or the crash of oceans. It was a small chirp, almost playful, yet within it was written the collision of giants. For the first time, humanity had not only seen the universe with light, but had heard it with gravity. It was as though the cosmos had added a new sense, another channel through which to tell its story. To understand what happened in that moment, think again of the pond. 2 heavy stones dropped together create ripples that meet and merge, producing a pattern stronger than either alone. In space, when black holes spiral into one another, they create ripples in space-time itself. These ripples travel outward not across water, but across the geometry of reality. When they passed through Earth, every atom, every person, every clock shifted ever so slightly, stretched and squeezed by less than a fraction of a proton's width. None of us noticed, of course. The effect was far too small for human senses, but the lasers in LIGO noticed, and their quiet record gave us a new way of seeing. Since then, more detections have followed. Black holes colliding, neutron stars spiraling together, sending out both gravitational waves and flashes of light. Each event adds to our understanding, like hearing different notes in a new instrument. We now know that the universe is not silent but humming, filled with ripples from countless cosmic dances. These waves are not random. They carry information about their sources. From them we learn the masses of black holes, the distances of collisions, the very fabric of space-time tested in conditions we cannot replicate on Earth. The poetry of it is undeniable. For billions of years these ripples have travelled, carrying news of cataclysms we could never witness directly. They passed through galaxies, threaded the cosmic web, crossed voids, and finally arrived here, brushing past you as you sit or lie listening tonight. You felt nothing, but your world shifted by a fraction, a whisper of gravity's voice passing through your body. You were touched by an event that happened before humans even existed, before the Earth had cooled into continents, before life had begun. Straightness dissolves here once more. Time and space do not remain rigid, do not hold to absolute measures. They bend and flex, trembling briefly as waves move through them. The very rulers we might use to measure length, the very clocks we might use to measure time, are stretched and compressed. The universe does not honour straight lines, even in its quietest fabric. It ripples. As you think about this, imagine lying beside a pond, listening to the soft lapping of waves at the shore. Each wave is a message from something far away, carried gently but persistently. The night sky above you is another pond, and the ripples of space-time pass through it silently. We cannot hear them without delicate instruments, but they are there, forever reminding us that even the firmest things we imagine, space, distance, time itself, are capable of flowing like water. So the next time you hear the chirp of a bird in the morning, you might remember that the universe has its own chirps too, small signals carried on gravitational waves, announcing that somewhere, 2 stars or 2 black holes embraced in their final spiral. And though we notice only faintly, though we must strain to detect it, the ripple reaches us all the same. You're part of a cosmos that does not hold still. It curves, it bends, and when stirred, it ripples like a pond beneath a falling stone. There is something comforting about the word now. It suggests a shared moment, a single instant we all inhabit together. You might imagine that as I speak these words and you hear them, we are both placed into the same frame of time, sharing one slice of reality. For much of history, that was the assumption, that now was universal, a straight and absolute line stretching across the cosmos, touching all things at once. But relativity, as it so often does, quietly removes that comfort. It shows us that now is not the same for everyone, that simultaneity, the idea that two events happen at the same time, is not absolute. To hold this gently, picture a long train gliding along its track at night. At its midpoint sits a passenger, quiet, perhaps reading under the dim glow of a lamp. At that exact moment, lightning strikes both the front and the rear of the train. The flashes leap out into the darkness, and the passenger in the middle looks up. If the train were not moving, the light from both strikes would reach the passenger at the same time, and they would conclude the bolts were simultaneous. But because the train is in motion, the passenger is moving toward the light from one strike and away from the light from the other. The beams travel at the same speed, but one meets the passenger sooner than the other. From their perspective, the strikes were not simultaneous at all. Meanwhile, an observer standing by the track sees it differently. From their vantage, the passenger is moving, but the strikes were equidistant, and the light travelled equally to the midpoint. To them, the strikes were simultaneous. Both perspectives are correct. The disagreement is not about perception or error. It is built into the fabric of space-time. Simultaneity depends on the observer's motion. Now for one may not be now for another. You can soften this abstraction by thinking of two friends watching fireworks from different hillsides. One sees a burst slightly sooner because the sound travels differently across valleys, while the other insists on a different order. Both are describing what they experienced, and both are right, though the truth is more complex than either version. Relativity tells us that at cosmic scales, such disagreements are not about sound or delays, but about time itself. There is no universal referee to settle the matter. Each now is local, curved by motion, personal to the observer. In everyday life, the differences are too small to notice. Our speeds are modest, our distance is tiny compared to light's pace. We can agree easily on what happens when, but at high speeds or across great distances, the straight line of simultaneity breaks apart. Imagine two astronomers watching distant supernovae from different corners of the galaxy. One may insist that star A exploded first, while the other swears that star B did. Both are telling the truth from within their own frame, yet their truths diverge. The universe does not privilege one over the other. There is no single order that is correct everywhere. This can feel unsettling. We are used to time being a shared fabric, a common thread stitching us together. Relativity reminds us instead that it is more like a patchwork quilt. Each observer holds their own piece, stitched to others but never perfectly aligned. Straight, universal now dissolves into a mosaic of curved nows, overlapping and shifting. There is a kind of beauty in this too. It means that your experience of time is uniquely yours, shaped by your motion, your position, your journey through space-time. No one else has exactly your sequence of nows. Life is personal not only in memory and feeling, but in physics itself. Your heartbeat belongs to your frame, your laughter to your seconds, your story to your thread. Others see you differently, but neither account is wrong. The universe allows many truths, each curved into its own perspective. To imagine this more softly, think of two people describing a sunset. One stands on a mountain ridge, the other in a valley. To one, the sky darkens earlier, the colours shifting sooner. To the other, daylight lingers. Both point to the same sun, yet their horizons are different. Their now is not shared, though they speak as if it is. Relativity tells us that the same is true on every scale. Our horizons, defined by motion and position, give us our private sunsets, our private moments, none more real than another. What does this mean for our sense of connection? Perhaps it means that what we call now is less about an absolute instant and more about shared experience. When you sit with someone over tea, the comfort does not come from knowing that your seconds are aligned with cosmic precision. It comes from the warmth of presence, the overlap of your personal threads. Physics may say your nows are different, but meaning says they are together. And so, straight simultaneity, one global now for all, becomes another illusion. The universe bends it away, replacing it with relativity. Two lightning strikes can be both simultaneous and not, depending on who tells the story. Two travellers can disagree about order and both be right. Straight lines dissolve again, this time not in space or in motion, but in the very fabric of time's present. As you close your eyes, perhaps you can think of your own now as one lantern glowing softly in the dark, shining in your small region of space-time. Somewhere else, another lantern glows, slightly offset, its light not perfectly aligned with yours. Together they form a constellation, not a single beam, but many, curved into a pattern that makes the night more beautiful than a line ever could. When we talk about the future and the past, we often imagine them as lines. Behind us stretches the past, a long straight record of what has already happened. Ahead of us extends the future, a line still unwritten, waiting to be filled. We picture ourselves as standing in the present, a thin slice cutting between the two, moving steadily forward. It feels simple, tidy, and comforting. Yet, once again, the universe complicates this picture. Time does not unfold as a single straight ribbon shared by everyone. It unfolds as a set of possibilities bounded by light, shaped into cones, and arranged not like a line but like a sculpture. To see this softly, imagine yourself holding a lantern in a thick fog. The glow spreads outward in a cone, illuminating what lies within reach. But beyond the cone, the fog remains opaque, hiding what you cannot touch with your light. This is how space-time arranges your future. From your current place and moment, you can influence only what lies within your forward light cone, the region that light, or any signal slower than light, could possibly reach. The rest outside the cone is forever inaccessible, no matter how much time passes. Your lantern cannot cut through the fog there. Your past is arranged the same way. Look behind and imagine a second cone stretching backward through the fog, narrowing to the tip where you stand. That backward cone contains all the events that could have influenced you here and now. The light of a distant supernova that left its star millions of years ago and just reached your eyes tonight belongs to your past light cone. A star even farther away whose light has not yet arrived lies outside your reach, forever excluded from your present. You're stitched into a geometry where what is real for you depends not only on when, but also on where. This is what physicists mean when they say that causality is bounded by light cones. They are not abstract diagrams, but real lanterns in the fog of space-time. They define which events can talk to one another and which are silent forever. Two observers standing in different places may have overlapping cones but never identical ones. Their pasts differ, their futures differ, and the intersection of their lanterns defines the sliver of reality they can share. Straight universal time dissolves here again, replaced by curved regions of possibility. From this geometry arises another striking vision: the block universe. Instead of thinking of time as flowing, the block universe imagines all moments existing together, like a great sculpture. The past, present and future are not separate entities passing by one another, but pieces of one whole structure. Your birth, your listening tonight, your final breath, all exist somewhere within the block. You, walking through life, are like a thread woven into its fabric, moving from one coordinate to another, but never leaving the sculpture. The flow you feel is personal, but the block itself is timeless. At first glance, this can feel unsettling. If all moments already exist, then what becomes of freedom? Where's the sense of becoming, of surprise, of change? Yet think of it another way. Imagine a symphony written on sheet music. All the notes already exist, spread across the pages. The beginning, the middle, the end. They're all there at once. But when a musician plays, when an orchestra unfolds the notes, the music flows, one phrase at a time. You are the musician of your own thread through the block. The symphony exists whole, but you still live it in sequence. The sculpture is complete, but you still walk its corridors step by step. In this view, straightness once more reveals itself as an illusion. We think of life as a straight arrow of moments, all sharing a common now. In truth, each thread curves within the block, each light cone shapes its own possibilities. What is now for you may not be now for someone light years away. And yet, together, all those nows exist as part of the same sculpture. To soften the thought, imagine a quilt stitched from countless patches. Each patch is its own moment, its own pattern, its own now. Alone, it may seem incomplete, but together they form a whole design. You're not outside the quilt, watching it be assembled. You're inside it, part of the stitching, carried along as thread. The quilt does not change once finished, but living within it, you feel the journey, the unfolding of its colours. The block universe is such a quilt, infinite in scale, with every patch a piece of space-time, every thread a life, every curve a story. There is comfort here too. If every moment exists, then none are lost. The laughter of a child, the glow of a first sunrise you ever saw, the warmth of a hand you once held, all remain within the sculpture. They do not vanish. They are not erased by time's march, because time does not march. It simply is. You may move past them, but they remain, part of the great structure that holds everything. As you drift tonight towards sleep, think of your own lantern in the fog. Its light defines the part of space-time you can touch, but beyond it lies a vast sculpture, intricate, eternal. You're a thread weaving through it, moving in your own curved way, never straight, never absolute, but always real. Straight lines promised us a universal now. The universe gave us lanterns, cones, and a quilt, and in their softness lies a truth more enduring than straightness could ever be. For all that the universe resists straightness, human beings have spent much of their history chasing it. Perhaps it is because our world is so filled with curves, with rivers that bend, trees that branch, clouds that wander, that we long for something more certain, something we can draw with a ruler and trust will not deviate. Straight lines to us are not only tools but symbols of clarity, of stability, of order carved out of chaos. And so, we build them everywhere. Consider the roads of a modern city. Look down from an airplane and you may see avenues stretching like arrows, crossing each other at perfect right angles, forming grids so precise they could have been etched by a draftsman's pen. These lines make navigation simple, but they are not natural. Left to itself, a road meanders like a river, finding its way around hills, along valleys, through forests. Only with effort, with bulldozers and blueprints, do we force the earth into straightness. And even then, nature quietly resists. Asphalt buckles under heat, concrete cracks with frost, bridges sag beneath their own weight. What we build straight, the world bends in time. Architecture too reflects our hunger for lines. We raise towers in perfect verticals, lay beams in perfect horizontals, and admire the sharp geometry of walls and windows. The symmetry comforts us, as though we had imposed certainty upon the wild. Yet here as well the universe resists. Steel expands in the summer sun and contracts in the winter chill. Earthquakes shift foundations. Wind makes even the tallest skyscrapers sway, imperceptibly to those inside, but real nonetheless. Straightness, though drawn in blueprints, bends under the hand of gravity and the flow of time. Even our simplest tools betray the same story. A wooden ruler, when new, may seem perfectly straight, but wood is a living memory of a tree, and with humidity and age it warps, bows and twists. A metal bar, forged to be level, sags under its own weight if supported only at its ends. Engineers know this, which is why they design beams with curves to compensate, arches that distribute forces, bridges that rise and dip to hold their shape. Our straightest structures endure only because we secretly embed curves within them, aligning with the universe's preference rather than defying it. On paper, straight lines are easier. A pencil glides along the edge of a ruler, and the graphite leaves behind a mark that seems certain, unwavering. Yet even there, under magnification, the line is not truly straight. The fibres of the paper rise and fall, the graphite grains scatter irregularly, the edges blur. The line only seems straight because we do not look too closely. At larger scales, too, our straight borders on maps are illusions. Political boundaries drawn with rulers, slicing across deserts and forests, ignore the curves of rivers, the slopes of mountains, the wanderings of people. On the ground, those straight borders are lines in imagination only. The land itself curves regardless. Perhaps this is why straight lines hold such power for us. They are rare. They feel like triumphs over the natural world, like statements that we have imposed our will on something larger and wilder. To walk down a perfectly straight road feels like walking inside an idea made real, a geometry imposed on chaos. But just beneath the surface, the universe waits, curving slowly, gently, undoing the illusion. There is also a psychological comfort in lines. We speak of wanting a straight answer, a straightforward path, a life that is on the straight and narrow. Straightness, in our metaphors, is honesty, simplicity, virtue. Crookedness, by contrast, is deception, complication, difficulty. Yet nature thrives on crookedness. Rivers that meander sustain fertile floodplains. Branches that twist offer shade. Roots that spread unevenly anchor trees against storms. What we call crookedness, the universe calls life. None of this is to say that our pursuit of straight lines is wrong. It has given us roads and bridges, cities and towers, order in the places we needed it most. But it is to say that straightness is not the universe's language. It is ours. And whenever we speak it into the world answers back in curves. The bridge sags, the tower sways, the map line dissolves into rivers and hills. Straightness must be maintained constantly, repaired, redrawn and reinforced. Left alone, it bends. If you glance around the room where you are now, you might see many straight edges. The table, the shelves, the frames of doors and windows. They seem steady, comforting in their clarity. But remember that each of them is bending in ways too small to see, sagging under weight, expanding with heat, warping with age. Even your floor, which feels flat and solid, bows slightly under gravity. The straightness is temporary, a momentary illusion, held against the grain of the universe. There is perhaps something humbling in this. We seek perfection in lines, but the universe insists on curves. Our straightest roads are eventually swallowed by vines and soil. Our straightest walls are softened by wind and rain. What we build is not wrong, but it is temporary. The cosmos has more patience than we do, and in time, it always wins. So tonight, as you look at the edges around you, at the neatness of the room, at the grid of streets outside, you can appreciate them for what they are, our attempt to bring order into a curved world. But you can also smile at the knowledge that the universe, quietly and without hurry, is bending them back toward its preferred shape. Straightness may be our language, but the universe replies in arcs. We have spent much of this journey looking outward, at planets orbiting, at satellites circling, at galaxies woven into filaments, at black holes and neutron stars bending time itself. But the universe's preference for curves is not confined to the grand scales of astronomy. It reaches inward too, shaping the way we live our lives. When you look carefully, you find that your own path through the world is not straight. It bends, it loops, it branches, it meanders like a river, coils like a shell, spreads like a tree. Consider memory. We often picture it as a timeline, a straight sequence of events recorded one after another. Yesterday follows the day before, tomorrow follows today, and we imagine ourselves moving steadily forward. But memory does not work that way. It bends back, looping us into past moments without warning. A smell of bread might pull you suddenly into a childhood kitchen. A song might transport you instantly into the presence of someone long gone. The straight arrow of chronology is bent by memory's spirals. You're never simply here and now. You're here with layers of then curling around you. Your life is a spiral staircase of recollection, each step forward accompanied by echoes from below. Choices too refuse straightness. We talk of being at a crossroads, of having a clear fork in the road, but the truth is more like a branching tree. Each decision you make divides into new branches, and those branches divide again. Your life, looked at from above, would resemble a forest of possibilities. Some branches pruned, others flourishing, many curving away from the trunk you once thought you were following. Straight ambition may sketch a clean line from beginning to end. Study this, become that, achieve here, arrive there. But reality adds detours, surprises, bends in the path. And those bends, though they may frustrate in the moment, are often where life becomes most alive. Think of ambitions written on paper. They look neat there, tidy as straight lines drawn with a ruler. But lived experience is closer to a meandering river that cannot help but curve with the land it crosses. Opportunities arrive unexpectedly. Losses alter direction. Joys appear where none were planned. To insist on living in straight lines is to fight the current. To accept curves is to float with it, allowing the river to carry you where it flows. Even relationships follow this geometry. You may meet someone by chance, your paths crossing at an angle neither of you could have predicted. The line you thought you were on bends as you walk beside them. Sometimes you part, your paths diverging into different arcs. Sometimes you loop back, finding each other again. These encounters are not plotted on graph paper. They are drawn in spirals and branches, with loops of reunion and branches of separation. To love is to allow your line to bend, to reshape itself in harmony with another's. Our very bodies carry these curves. Your ribs arch into a cage protecting your lungs, while your veins and arteries spread like rivers through a map. Your DNA coils into spirals, the very code of your being written in curves. Straightness is absent in your body, replaced by patterns that fold, loop, and branch. You're made of curves, living in curves, thinking in curves, even when your mind craves straightness for comfort. This does not mean that straightness is worthless. A straight path can be useful, a goal can be clarifying, a promise of direction can give you courage. But it is worth remembering that such straightness is always provisional. The world will bend it. Your memories will loop, your choices will branch, your ambitions will curve. Straightness is your sketch. Curves are the universe's revision. Perhaps this is why we find beauty in curved objects, in arches of bridges, in winding trails, in the spiral of a staircase, in the loops of handwriting. They resemble the truth of our lives more than a ruler's edge does. Straight lines feel efficient but harsh. Curves feel honest, forgiving, alive. To imagine this more softly, picture your life as a garden path. You may have drawn it on paper as a single line from gate to door, but when you walk it, you find it winding past flowers, turning around stones, looping beneath trees. It is slower than you planned, less direct, but richer. The detours allow you to notice scents, textures, and colours you would have missed. That is how lives bend. What we thought of as crookedness often becomes meaning. And when you look back, you will not see a straight road behind you. You will see loops of memory, branches of choice, spirals of love and loss. It may look tangled, but in its tangle lies its truth. The straight story would have been false, the curved one is real. So tonight, as you lie with your thoughts drifting, remember that you are not failing when your life does not follow the straight lines you once imagined. You are following the universe's preference, bending and branching as rivers and trees do, spiraling as shells and galaxies do. Straight lines belong to our diagrams. Curves belong to existence. Your life is not a straight path, but a curved one, and in those curves lies its beauty. We have wandered far together tonight. We began with the imagined straight lines of human design, train tracks stretching into the dark, rulers held against paper, grids of streets and cities. We watched as the universe bent those lines, curving orbits, weaving filaments, spiraling galaxies, branching rivers, and even bending time itself. Again and again, the straight paths we imagined dissolved into arcs. The story the cosmos tells is not written in rigid strokes, but in loops, spirals, and webs. Straightness is our invention, while curves are its truth. Think back over the places we have passed. We saw Einstein's insight that space and time are not separate but a single fabric, and that mass curves this fabric until even light bends. We followed clocks flown on airplanes, ticking differently than those left behind. We looked at muons raining from the atmosphere, living longer than they should because speed slowed their time. We visited GPS satellites circling above, their clocks needing daily corrections because Earth's gravity and their velocity pull in different directions. Every one of these examples reminded us that straight time does not exist. Motion and gravity bend it always. We moved then into the natural world, where curves fill every corner of life. Seashells grow in spirals, hurricanes swirl across oceans, galaxies unwind their arms across space. Trees branch, rivers divide, lightning forks, lungs fill with bronchi. Fractals repeat complexity at every scale, never straight, always detailed, always curved. Even at the grandest scale of all, galaxies gather not in rows but in filaments, forming a cosmic lace stretched across billions of light years, with voids between like dark windows in the cloth. Straightness was nowhere to be found. At the extremes we looked at black holes where time tells two stories at once, frozen to the observer outside, smooth to the traveller falling in. We listened to neutron stars pulsing, their clocks slowed by gravity, their beams marking the slowed heartbeat of dense matter. We felt ripples of space-time pass through us, gravitational waves stretching and squeezing Earth itself, though we could not sense them without delicate instruments. Everywhere we looked, straight lines gave way to bends. We then let philosophy enter quietly. We saw how simultaneity is not universal, how two lightning strikes may be simultaneous for one observer and not for another, and both accounts are true. We imagined light cones as lanterns glowing in fog, defining which events are reachable and which are forever hidden. We pictured the block universe, all moments existing together like a sculpture, with each of our lives a thread winding through it. Even our own sense of now turned out not to be straight or shared, but curved, personal, bounded. And finally we returned inward to the lives we live. We saw that we too build straight lines, roads, towers, blueprints, metaphors of honesty and simplicity. But nature bends them, sagging beams, swaying skyscrapers, warping rulers, crumbling maps. We saw that our lives, despite our attempts to plan them straight, unfold as spirals of memory, branches of choice, arcs of love and loss. What we once thought crooked is often what gives life its richness. Straight ambition is softened by detours. Straight timelines are looped by memory. Straight roads are interrupted by encounters, by laughter, by grief, by joy. It may sound as though the universe has been scolding us all along. Do not draw your lines, for they will bend. But perhaps the lesson is gentler. Perhaps it is simply saying, curves are where life happens. Do not fear them. The bend in a river nourishes the land. The spiral of a shell protects the creature within. The branching of your lungs keeps you alive with every breath. The loops of memory keep those you love close, even when they are far. The arc of your life, though not straight, is still true. There is comfort in this. Straight lines promise certainty, but certainty is brittle. Curves promise change, adaptation, resilience. They soften what would otherwise break. They allow journeys to continue when straight paths would end. And perhaps that is why the universe prefers them, why in its greatest structures and tiniest details it always bends. So tonight, as you let yourself drift toward rest, you might imagine your own life not as a straight arrow but as part of a spiral, widening gently with each year. Or you might imagine yourself as a branch in a great tree, diverging and dividing, yet still connected to the whole. Or perhaps you're a bead of dew caught on a thread of the cosmic web, glistening for a while before sliding down the filament. In all these metaphors, the lesson is the same. Straightness was never required. The beauty lies in the curves. Our journey has been long, but perhaps you feel it has also been slow, as if time itself softened while we travelled. That is fitting, for the story of straightness dissolving into curves is also the story of time flowing differently, stretching here, compressing there. If your eyelids have grown heavy, if your thoughts have spiralled into dreams, then you have joined the universe in its favourite habit, bending. And so, we close. The universe does not draw in straight lines. It swirls, it loops, it branches, it weaves, it writes its poetry in arcs, and within those arcs we live, we breathe, we remember, and we sleep. Our exploration has softly ended. Time flows forward, but I hope tonight's slowed for you. Rest well.